Good morning, Warriors. Today is lesson 11.3. Today we're solving exponential equations and logarithmic equations. Our essential ideas today and tomorrow, for that matter, that we're looking at is analyzing different strategies to solve exponential and logarithmic equations because it depends on how it was given to you, how you were going to solve it. Before we go there, let's get the engines turning here with a couple warm-up problems quick. Expand these two problems. I would hit pause, try them on your own, and here come the answers. And then the next two warm-up problems will be condensing. Condensing is a very important part of solving logarithmic equations, so I would encourage you to pause the video and try to condense these two to make sure you're condensing them correctly. And here are the answers that you should get after you condense. Okay, moving right along here, we're coming to the next page, solving an exponential equation. Bottom line, anytime we have a variable in the exponent up here, what we have found over the years, most students prefer the basic strategy of rewriting the equation into logarithmic form. We did this earlier for ACT review, and just to give you a short refresher here, how we do that is we have the base of an exponential equation. So we have a base and exponent that equals an argument. And if I translate that into a logarithmic equation, we have log, we have log. The base of the exponent goes in the base of the log. The argument goes inside the log. And logs actually equal the exponent. So we're going to need to be able to flip from exponential to logarithmic, logarithmic to exponential in order to solve these equations. Okay? And we're going to move here to our next page. Our next page is, how do we solve an equation when the bases are the same? A lot of times this is just getting the bases to match. Getting common bases can be established. Many times it is not established. But if I run into what I have up there, okay, I can correlate 9 and 27, those are both base 3. So I can rewrite 9 as 3 squared. That's going to get raised to the x power. And I can rewrite 27 as 3 to the third power. Remember, a power to a power, this is 3 to the 2x equals 3 to the third. And if my bases are the same, all I really need to do is set my exponents equal to each other and solve. So x would be 3 over 2 in that case. Okay. Number 2, a little bit harder, but I'm correlating the 8 and the 4. Okay. So I'm first looking at it as 8 to the x equals 4 to the negative 1 power, because I don't want a fraction if I don't have a fraction over here. Well, 8 and 4 can both be written as a base 2. 8 is 2 to the third power. That's going to go up to that exponent of an x, and 4 can be written as 2 squared to the negative 1. I take my power to a power on both of those, and I have 2 to the 3x equals 2 to the negative 2. Once my bases are the same, I just need to set my exponents equal to each other. 3x equals negative 2. So in this case, x actually equals negative 2 thirds. Okay. And in the next portion of the video, you are going to see, what do we do when the bases of a log are the same? Sorry, actually, the question wasn't if the bases are the same. What happens if I have just a log on each side of the equation? What do I do? Well, if I look, if that's a log base 2 and that's a log base 2, as long as these logs are the same base, what I can do is I can set their arguments 4x minus 3 to equal 13 and solve. So I get 4x equals 16. So x would have to equal 4 in this case, would solve that one. Now over here my bases aren't the same, okay? But if I look, this is a log base something of 81, and this is a log base 7, 3 to the 4th power. Well, that's just 3 to the 4th power is 81. So because my arguments are the same, all I have to do is set the bases equal to each other for the log. 3x minus 2 equals 7, and solve that equation. 3x equals 9, so x would have to equal 3 in that case, okay? And as I'm moving across there, I do want to move to my next page. I have those, and at the bottom of your page, all these notes you can print on the blank notes if you can. But something that's very important here, remember when solving logarithmic equations, there are restrictions involved with both the argument and the base. The restrictions are the base of a logarithm, okay? So the base of your logarithm has to be positive, and it cannot be 1, okay? The argument of the logarithm in the end must be non-negative. So it has to be non-negative. It has to be greater than 0. So the argument cannot be 0 either. So when you're looking at a log base b of a, this b, that b has to be a positive number, and it cannot be 1. In a, your argument has to be a non-negative positive number. Anything. This can never be negative in the end for a number, okay? And from there, we are going to come back to my notebook, and we are going to move along here. And, well, what happens if the exponent is unknown? Well, that's typically what we do. There's two things of work here. Okay, I can do it the complicated way on the left side, or I can just look at 8 to the x equals 145. Well, 8 is not a power of 145. So what I'm going to do is I'm going to switch the form of 8 to the x equals 145. That equals a log base 8 of 145 equals x. So the left side, log base 8 of 145, that's just a number. And in order to get that, we have to remember our change of base formula that we had. And the change of base is the log of the guts. So I'm going to take a log base 10 of 145, and I'm going to divide that by log base of whatever that base is. So log 8. And if you take a log 145 divided by a log 8 in your calculator, you will get approximately 2.39. We're going to round everything to 3 decimal places, though. So this is the choice that most students take. So what we're going to do is we're going to look at a couple examples here. And sometimes you need to do a little more manipulating before you can switch forms, as you see here. Bottom line, what I want to do is I want to isolate that exponential equation, the base of the exponent with its exponent. I want to isolate that, move everything to the other side. That's the only time I can change form. Okay, so I'm going to hit pause and write a couple examples on my board. So this is just 3 examples of solving an exponential equation when we do not know what the exponent is. So we need to isolate the exponent. So we're going to add 5 across. We have 4 to the x minus 3 equals 21. Now, because I don't know what that exponent is, I'm going to change the form of this. This is going to be a log whose base is 4, okay, of the argument 21 equals the exponent x minus 3. So from here, what I'm going to do is I need to use my change of base here because I need a calculator. So I'm going to hit a log 21 divided by a log 4. That's what x minus 3 equals. Well, when you type this into your calculator, round it to 3 decimal places, we get roughly 2.196 is approximately what x minus 3 equals. So x has to approximately be, after I add the 3 across, 5.196. Okay. When I look at example 1, I got to get the exponent, the base and the exponent isolated. So I'm going to subtract 6. So I have 2 to the x minus 5 equals 24. I'm going to change my form from it to extract that exponent, that variable out, I need to change form. So this is going to be a log base 2 of 24. Logs equal that exponent, x minus 5. And then I'm going to have to do a change of base here, which is a log 24 divided by a log 2. That's what x minus 5 equals. I'm going to type this into my calculator. And I can't do it without my calculator. And when I do, I get this as 4.585 is approximately what x minus 5 equals. I add my 5 across, so 9.585 is approximately equal to x, and that's what x is. Okay, last one, an extra step going on here. First thing I got to do is I got to add that 40 across. So I have 7 times 2 raised to the 3x equals 840. And when I divide that by 7 now, I have 2 to the 3x actually equals 120. My exponential is isolated, so I'm going to get at that exponent, I'm going to extract it out by changing form into a log. This is going to be a log base 2 of 120. It equals my exponent, 3x. In order to find out what this log base 2 of 120 is, I'm going to change the base of log base 10 120 divided by log base 2 is what 3x is. You type this into your calculator, and we find out that that is approximately 6.907 is approximately what 3x equals. Divide both sides by 3. X is approximately equal to 2.305. Okay, so that's solving exponential equations when I do not know what the exponent is. And what I'm going to do now is I'm going to hit pause, and our next thing is we are going to solve one page of logs, and then we're done for the day today. Here for the next part, this is the last page of notes we'll be doing today. You should be on page 4, basically, where the argument of a log is unknown. Well, again, there's a couple ways to skin a cat, but if you look, okay, we have found most students, whether you start exponentially, you start log, okay? If your base is unknown of the log or the argument is unknown of the log, we have found most students prefer to change the form from a log into an exponent. So whenever either one of these are unknown, it turns into something I can solve in an exponential function. So log base 5 of x is approximately equal to 3.1. What is x? Well, x is what 5 to the 3.1 is if I change it into that. So it's 146.83. The ultimate goal that we're getting here when we're solving logarithmic equations is the goal is to get the log all by itself, just the log equaling a number on the right side, and then we rewrite the equation, okay? Examples, I got 2 examples here, and when I'm done with these 2 examples, I encourage you to try the next 2 before I do them and hit pause. So, again, I do not know what the argument is. I do know it's log base 2. Well, that's no big deal. Notice my log is already isolated. So because my log is isolated, I'm going to change this from a logarithmic equation into an exponential equation. So that means it's going to be the base to the exponent equals the argument. Okay, oh, I got a quadratic equation. Well, what's 2 to the 4th power? Well, 2 to the 4th power is 16 equals x squared minus 6x. Well, how do I solve a quadratic equation? Excuse me. Yeah, I got to set it equal to 0. So 0 equals x squared minus 6x minus 16. And factoring is always fastest when you can do it. You can't always factor things, but this one does factor. And it factors into x minus 8 times x plus 2. There's my x squared, there's my negative 16. Negative 8 plus 2 is negative 6. So then I can see my solutions are when x equals 8 and when x equals negative 2. Okay? So it is possible that you can get more than one solution. It just depends on the degree of the argument in here. If that were cubic, you could have 3. Okay? Number 2 is a little bit more entailed because I need to isolate my log first. So the first thing I'm going to do is I'm going to say, oh, that's 2 times a log 6 of x squared plus x. I'm adding that 8 across to get 2. I'm going to divide both sides by 2 to get rid of that, and I have a log base 6 of x squared plus x equals 1. Well, now my log equals a number. So I'm going to change the form into an exponential equation, which is the base of the log to the exponent equals the argument. Oh, that's not a 1, that's an x. Oh, it's another quadratic. So what I'm going to do is I'm going to subtract my 6 over and say 0 equals x squared plus x minus 6. Does that one factor? Why, it most certainly does. X, one's plus, one's minus, more positives, the negatives, x squared minus 6, I got 3 minus 2 for 1. So x must equal negative 3, and x must equal 2. Okay? So what I'm going to do here is I'm going to hit pause, and I'm going to rewrite my board for our last two examples. If you were able to print off the note sheet, give the next two a try. If not, as soon as the screen comes back on, write the problems down, hit pause, and give them a try at that time. These are our last two examples for today, and they are crafty little critters because remember how I said we want to get one log equal to a number. Well, now I have two logs on here equal to a number. Well, I can't change forms if I have more than one log written in an equation. So the trick to this is we need to condense these two logs, and because it's addition, I can say that's going to be a log. And remember, this is like a naked log. It doesn't have a base, and if the base isn't written, that's an automatic 10, base 10. But 5 times x, that gives me a 5x equals 2. Now I have one log equaling a number, and that invisible 10 is there. Now I can rewrite this in exponential form. So I can say 10 to the exponent equals the argument. Well, I know 10 squared is 100 equals 5x. So I got to divide both sides by 5. So x must equal 20 in that example. Okay. And number 4 over here, again, if you want to try it, hit pause, try the last one. I encourage you to do that. If not, notice I have more than one log. Again, I have to condense. But check it out. This one's minus. So now I have to divide the arguments. Okay? So this is going to give me a log base 5. And it's always the first argument divided by the second argument equals 1. I am to one log, so I could change form, but look, inside this argument, I could simplify that because I know 3 goes into 45, so I really want to look at this as a log base 5 of 15x equals 1, because 3 goes into 45 15 times. And what I'm going to do now I'm going to change the form of this, and I'm going to say the base to the exponent equals the argument. So I get 5 equals 15x. So x actually equals 5 over 15. Well, it's a fraction. You have to reduce it. So x in this case must equal 1/3. Okay? And tomorrow we have one more thing to look at, and that's when is the base unknown? How do we deal with that? And then we're just going to have a little conglomeration of problems I'm going to go through. I'm not going to do them all. I think there's a total of, it looks like 14 problems, of which I'm going to do maybe, I don't know, 6 or 7. And I'm going to leave the rest of them for you just to pull right off of the note sheet and give them a try on your own. And if you can't get them, the answers will be online. The worked out answers and the whole script of notes will be posted in It's Learning. So we will see you tomorrow, and have a great day.